Okay. So for this function, there's like the outside, which is like a cosine, and then the inside, which is the 7x, right? So when you're trying to do chain rule stuff, you basically are like, okay, let me say, if I'm trying to find the derivative of this, the general like rule for it is
Oh, yeah.
you do like outside derivative. So this means kind of prime and then inside times inside derivative, right?
Yeah, no, I remember that. I just didn't realize it was the chain rule. Thank you.
Oh yeah,
Sorry.
sure. Yeah, so whenever you sort of like have this, there's this ability to sort of like plug it inside. You always just basically like chain rule is just it's going to be prevalent. It's going to be a lot of over a lot of places. Even a constant continue like acts as like chain rule, right? However, if you had something like cosine of like x minus 4, like the derivative of this, what do you think? What do you think? So I don't like skip through it.
It's just
One.
one, isn't it?
No, just like the whole thing.
Sine of 1.
Negative sine of x minus 4 times 1
So negative sine of x minus 4.
times 1.
Yeah, times 1, right? Because you do this derivative of this outside, you keep this inside, and then you multiply it by the derivative of this inside. Does that make sense? Yeah. So that's just kind of like just the general sort of how you get through it in a sense. I don't know if that made sense.
No, it did.
It's like a chain of sort of doing this. So if you were to do something like ln of sine squared of like 3x, like this one's annoying, but you know you can do it. But it's a lot of chain rules over and over again, right? So the first term would be like 1 over just the sine squared 3x part, and then you multiply it by the 2 sine 3x, and then times, and then the cosine. Yeah, so it just kind of happens over and over and over again, if you will. So we can definitely
Got
do
it. Thank you.
future, and there will be chain rule problems like in the other examples that I can sort of like go through if that works. Yeah. Cool. Okay, I'm gonna erase this stuff. So critical points. Do you guys sort of know how to define those?
I kind of forgot.
Okay, so critical points are basically points where the function, say you have some function f of x. This is not okay. This is g of x. Ooh, okay. This is g of x. Critical points are either locations where you have local minimums or maximums, right? So here, etc. Or you have these inflection points where the f of x changes from being concave up to being concave down. So that's like like here, here-ish, here, maybe here. You see that? So there's a difference between these ones. That's like not. It's kind of like they don't have to be in the middle, but like drawing them in the middle is usually like a good way to do it. It's just how it happened to be, right? So how could you go about finding where these local minimums and maximums are?
Set the derivative equal to 0.
Yeah, exactly. So let's just do that. So f prime of x. What do we got here?
Three x squared plus 6x minus 9.
Yeah. Great. Okay. So we need to set this equal to 0. So I can just do that real quick. I'm gonna pull out a 3. And then you kind of run into a problem where, oh wait, no, you don't. I'm just being dumb. Okay. So how do you solve this? If you guys are doing it, that's perfectly fine too. Like you guys can do it on your own as well. I don't want to sort of.
I got x equals -3 and 1.
Yeah, that's great. 0 equals 3, and then 3 plus x plus 3 x plus 1. Right? So that's -3 x squared 3x minus x is 2x. Yeah, cool. So this is our factor, and then exactly, you just kind of like set them each equal to 0, and then you get x equals -3, x equals 1. Great. So if I plug this function in to Desmos or something, you'd see that at x equals -3 and x equals 1, you'd have those absolute maximums and minimums, right? So it'd be something like this is, wow, okay. Sorry. This is like 1, -3. It'd be, I don't know which way it is, but it'd be something like this. Yeah. Cool. And now you can kind of tell, like, actually, no. So cool. We found those the local maximums and minimums. So that's like only one part of the possible critical points, right? Because now we need to find those inflection points. Yeah. So how do we find those?
I know it has something to do with the second derivative, but I don't know what you do with it.
Yeah. So it's definitely something that you have to do with the second derivative. So if we just compute this real quickly, it's just 6x plus 6, right? So it's actually way easier than you think. It's the exact same thing that we did right here, except with the second derivative. Yeah. So you just set it equal to 0. And this one's pretty easy to solve for, right? Cool. Okay, so now we have our inflection point, which happens to be at the midway point between these two, right? But that's kind of irrelevant. So we have these critical points. I'm like 99% sure that these are both critical points. You might want to like double check that definition just in case for some reason they only think maximums and minimums are, but that's kind of besides the point. I'm pretty sure it's all of these. So
It's all values where it's either 0 or undefined, I think.
okay, cool. So yeah, we don't need to worry about undefined because this isn't this is just a polynomial, right? So we're good there. But if it was like a rational function, so it was over like something, it was over something where there's like x minus 1 on the bottom or something, then we need to worry about it. But we don't need to right now. So let's think. Are we good with like 2a? Because this was basically the entirety of 2a. Does that sort of make sense? Awesome. Let's go to 2b. So what does 2b state? I think it's like find where it's decreasing, right? So it wants us to find where f is decreasing. F. So I'm just gonna sort of, okay, wait. I'm gonna erase this because it might be misleading. So before I sort of like go into it, I just want to know where you guys think what you guys think our next step is for this problem. If we're trying to find the point with the interval for f where it's decreasing.
Drawing the number line.
Yeah. So you have that sign chart thing, right? So what are we gonna put on it?
Like the critical points.
Yeah, so we're gonna put on -3 and 1 there, right? Because -1 doesn't really have to do anything with decreasing or increasing. That's more concavity. Yeah. So I can just put in -3, 1, cool. And so now all I have to do is to find out, based upon these points, whether or not the, how should I say? Sorry, I'm trying to like think of how I should like explain this. So based upon these points, I want to plug in values in between them or outside of them to see if the derivative of f of x is positive or negative. Because if the derivative is positive, that means the original function is increasing. Whereas if the derivative of f is negative, that means it's decreasing. Yeah? Okay. So what's a point? What point? What's my like starter point that I could like plug into here?
0.
Yeah, so you plug in 0. So I guess I can just sort of like just keep it right here. So you plug in 0 here, 0, 0, -9. Okay, so we know that's going to be negative. Cool. What's another one? Maybe like 2. You can try 2. Right.
I did -4 and 2.
Yeah. So -4 works perfectly fine. So I guess we can start from up here. I'll show you a bit of an easier way to do it in a second, but like let's just start from here. So -4 squared is 16 times 3 is 48. -24 is 24. -9 is positive. So that's positive, right? Is that what you got? Cool. And then 2, I'm sure you've already sort of like plugged that in and found out.
I got it to be negative, or, oh wait,
So
never
4
mind. Yeah, no, I
plus 12 minus 9. Yeah, cool. Okay, cool. So then we can just kind of look at the point where it's negative, right? So between x values of -3 and 1, the derivative of f is negative. Therefore, the original function is decreasing. So there we go. I guess I can say well, I guess it's like this. Yeah. Yeah. So we just got this little interval. I'm pretty sure it's the parentheses because if it's at -3, then it's not increasing or decreasing because it's like a maximum. But now we can kind of draw out what this graph looks like, right? So if I wanted to just kind of do a little, actually, we'll save that till the very end. Okay. So before we sort of move on, I want to show you guys like a little bit of a quicker way to sort of do this whole sign chart thing. I know it's not that hard, but this is just much faster in my opinion. So what I like to do is basically take all the terms that I sort of have laid out right here at the very end where I found my roots, right? So I take this x minus 1 term, I take my x plus 3 term, and I write them out over here on the side. So maybe x plus 3, x minus 1, okay? And then rather than taking a value somewhere in these 3 regions and plugging them into here, and then seeing if it's positive or negative, all you have to do is plug it into each of these and then tell the difference. Because if you plug in, say, a number into x plus 3, that gets you a positive 1. But if you also plug one in to here, that gets you a -1, then those multiplied together are going to be negative, right? Or if this is negative and this is negative, it's going to be positive. Or if they're both positive, right? So let's like run through that really quickly. So say I want to plug in -4 because it's less than -3, right? So I plug in -4 here. -4 plus 3 is -1, so I know that's going to be negative. X minus 1 is -4 minus 1 is -5. So that's a negative, right? Because that was like -1 or whatever. This is -5. So these are two negatives, which would make it a positive. And you sort of like circle that, right? Then for the middle, say I do 0. 0 plus 3 is 3, so that's a positive. 0 minus 1 is negative. Multiply them together, get negative. And then, you do 2 or something. That's 5. That's 1. Positive. There you go. So that's how I like to do it. It's just a little quicker and sort of like you can kind of like see it all happen. Yeah. So keep that in mind. You can do that for when you're finding the maximum and the minimums or when you're doing the concavity. And we're actually about to do concavity in a second. So are we all kind of good on 2B? That sort of thought process. Awesome. Wait, sorry. I didn't know where. Okay. Okay, so C is asking us to find where F is concave up. So what am I looking at to do that?
The second derivative?
Yeah. So we're trying to find out where the second derivative is positive, right? Because wherever the second derivative is positive, F, the original function, is concave up. So that's kind of like your U. Whereas if this second derivative is negative, that's where it's down. Okay. So we already found this. We already found where the point is sort of going to be in the middle of our number line. And now we just need to basically plug stuff in out and around that. So draw our line, mark -1. And so to kind of use the method that I just used, in a sense, we're gonna use this x plus 1 term, right? So for the stuff that's going over here, because that's what's sort of said equal to 0, but that you can pretend this is more like the f of x. So it's whatever you have right before you find out what the actual values of x are. So I'll have like x plus 1. And then all I need to do is plug in 2 values, which I'm sure you guys are already doing right now, right? Yeah, so you can get that. Is that what you got? Cool. And so now we're just looking at wherever this is positive. And so we can tell that, okay, that's our interval for 2C. Yeah. Awesome. So from all this information, we can kind of draw a little bit of a nice picture for the graph, right? So let's see, we do this, mark 1, this is 1, 1, 2, -3, negative. Okay. So we know we're going to have an inflection point here. We're concave up over here, and we're concave down here. So we have like so this is how I sort of like to draw these things. I don't know if you can see it where. So from the left, from way on the left, we're increasing, and then once we hit -3, we're decreasing, and then we flip right when we hit -1. So I guess I need to like take this a little bit longer. Okay. And we're still concave down, and then okay, and then we go. Okay, so this is like our inflection point in a sense. It like isn't really well drawn, but this is sort of what it looks like. It's this idea. So like 1, -1, -3. Yeah. So does that sort of make sense how I sort of put all that together? Yeah? Okay. So are you kind of comfortable with this sort of method of basically just finding the derivatives, setting them equal to 0, and then knowing what they mean, really? Doing a little bit of application.
Yeah,
Yeah.
I remember there was also like another, oh, sorry.
No, you can go. It's fine.
I just remember there was like another part of it where it was like a graph of I think it was the second derivative. I don't really know, but it was like the relationship between the second derivative and the first derivative. And it was like, if it's like negative, like below the x-axis, then it like means something. And if it's like 0, like on the x-axis, then it means something. And then if it's positive, then it means something. Does that like sound familiar?
Yeah, for sure. So the way that we can think of the second derivative and the first derivative's correlation, rather than just the first derivative to the originals and the second derivative to the originals correlation, is that the second derivative has the exact same relationship with the first derivative as the first derivative has with the original function. Yeah, because it's just a derivative, right, of the first one, right? So whenever we have, something positive in this second derivative, that means that we're increasing in this first derivative, right? Because whenever in the first derivative we have something that's positive, we'll also have something that's increasing in the original, right? So as long as you can sort of remember the relationship between the first one and the original functions, then you will inherently be able to understand the differences between the second and the first, because it's the exact same relationship, 100% the exact same. Does that sort of make sense? So like, if we're dealing with this, so what we can kind of tell is that, this is a quadratic formula. It's a quadratic equation, right? This first derivative. So we can even draw a little picture of the first derivative based upon what we know here, right? So if I were to sort of draw this out, this is -1. We're decreasing on the first derivative until we hit -1, and then we're increasing right when we hit after -1. Sorry, that was probably explained, right? So we come from the left. Okay, I'll just drop them over here. Come from the left, and we're decreasing, up, and then we hit -1, and then we try to do that. Okay, I'm just gonna move this. Awesome. Right? And that's sort of what our function looks like. Does that make sense? And so if you took
Yeah,
the derivative of
thank
this
you.
again, you could then tell that, it's just 6, right? And that's always positive, right? And so this is the second, and that's the second derivative of the first derivative, which would mean that this tells us the concavity of the first one, right? And as you can tell, this is always positive. How's that concavity looking, right? So it all sort of like works together in a sense, it's really cool. Does that sort of like answer your question a little bit?
Yeah, thank you. That
Are we
makes a
gonna-
lot more sense.
Are we gonna have to be able to identify like first and second, the original function, the first derivative and the second derivative from graphs, or will we be given like functions and then be told to find? Do you know what I'm saying?
Yeah. So you can it's definitely possible to do it both ways. The only times you guys are going to be given the only kind of functions that you'll be given as a graph, and then we'll sort of have to be able to tell, okay, this is, I'm going to erase this on the bottom here. Say I have this graph like this, kind of looking like here. And then that's like f of x. And then you can, be given a bunch of different choices for like f prime of x. This is like a. This is like b. Or something like. Is that what you're trying to talking about?
Yeah.
So I definitely think this skill of being able to recognize between the two and between even the three, although it will mainly just be the two, I think that is important. And you should definitely sort of like be semi-comfortable with it. However, again, you'll have, it's not proctored, and they say that you can use the calculators on Desmos, and they don't specify which. So, they have a graphing one. But I will say that, you can basically just use these concepts that we just learned, that we just went over, and just apply them very directly to this, right? So if this is f of x, then we know that, okay, when it's increasing, that's when our derivative function is going to be positive. And that when it's decreasing, that's when our derivative function is going to be negative. And then again, once it's increasing, that's when it's going to be positive, right? So if this is at like -1, or I guess this is at -2, this is at -1, right? I can kind of just guess what this function is going to look like. So say I have -2, this is 1. Okay, I know it's going to be positive before -2, okay? So it's like positive, in between it's negative, and then after the right, it's going to be positive again because it's increasing. So I can kind of just be like, okay, it's going to look something like, that. Yeah. So that's like, that's like, I think that's manageable. Just sort of being very explicit, like drawing everything out, being like, okay, this is where it's positive, this is where it's increasing, this is where it's concave up, things like that. And just knowing what to look for in each of the different, derivatives. That's how you're going to figure out these problems, and that's how you know you're going to be golden, I think. And then if you're going from this function, this derivative function, and then going up, you can sort of guess as well, right? So if I was going from this f of prime of x, and then they wanted me to find what f of x was in the first place, I could say, okay, well, I know that it's increasing at first, and then it's decreasing, and then it's increasing, which means that, there's going to be this local maximum right here at -2, and then there's going to be another local minimum right here at 1, because it's going to be, again, like increasing and then decreasing and then increasing. So it's going to sort of form that little path. So it's hard to see, I understand, but it's all about like the x values. The y values don't mean shit. Like honestly, like they really don't mean, because this sort of path could be the exact same if I, factored like a 3 out of the derivative or whatever, or like multiply this whole function by like 30. It would be the exact same sort of path in a sense. It would just be like, like scaled upward or something. So it's all about the x values. It's very important. That sort of give you a good sense of that. I know the graphing is weird, but it's basically just like doing this stuff, but like thinking about it, like looking at it, sort of. So cool. Are you guys good to like move on from this? Yeah. Awesome.
Yeah.
Okay, so let me just go through 3 real quick. This might take me a second because I know related rates are kind of rough. So I think I want to just like take my time by going through this, because again, like this is one of the harder problems on here. I remember like walking out of my final, it's either my final or I forget, it was something in calc, and everyone was pissed about how hard the related rates problem was. So I think the most important part of it is just being able to recognize when you have to sort of use that idea, And then same with optimization. Have you guys have encountered related rates, right? Like I'm not just like making this up. I didn't skip it or anything. Just like,
I honestly, I don't know. I got optimization and rates. I don't get.
okay, yeah. So optimization and rates are very, very similar. I'm gonna go over a related rates problem right now. We don't have an optimization problem on here, but honestly, optimization is kind of just an easier version of related rates. So I think that if you figure out related rates, optimization will sort of like fall into place naturally, if that makes sense. Okay, are you guys like looking at the problem, or should I like write it out a little bit?
I'm looking at it.
Okay, cool.
Yeah, I'm looking at it too.
Awesome. So the best thing to do with any of these word problems with like shit moving around, like birds flying, whatever, is to draw a picture. Every single time you should draw a picture. It'll just end up being a nice little like shape or something. And I think you guys know how to find like the perimeter of like a square and triangle. I mean, just like take a guess. So, or like even if it's like a circle, you know, I feel like you guys can do those things. And it just sort of like makes it a bit more easier to sort of like conceptualize. So I'm going to try to just start by drawing this problem out very explicitly. So we have a bird flying horizontally at an altitude of 80 meters. Okay, so we know a couple things from that. What are the two pieces of information that we have? I can also just like draw it out if that's like too like open-ended. So the first things first, that we know we have a bird that's kind of going in this direction, right? And then it's like 80 meters high. Okay, so we got some information. Cool. And the bird is flying at a speed of 500 meters a minute. Awesome. So we can kind of like put velocity to it. If the bird flies directly over a hunter, so I'm just gonna like draw a little character down here. Okay. What they want to know is the distance from the bird, they want to know how fast the distance between the bird and the hunter is changing when the bird is 100 meters away from the hunter. Yeah. So what would be the distance between the bird and the hunter here?
100.
Yeah, so I can just kind of like draw this line, right? Cool. So that's like 100 meters. Awesome. And again, this is kind of like 80 altitude, right? So it's like this. Okay. So what does that look like? It's a triangle, right? So that's how we're going to be setting up this whole thing. Is we're looking at the different parts that sort of make up this triangle, as well as their rates of change with respect to time as time goes on. Because what they've given us in the problem is the speed of the bird, right? So as this bird is sort of moving along, not only is, you know, its position changing, but its position with regards to the hunter is changing, right? So like, you know, in a second, it could be like right here, it could be right here, it could be right here. Like these are all different lengths. And so the length, this length specifically, how do I do this? Like that one, that's changing over time. And so that's what we're looking for, right? Does that make sense? So that's sort of like, you sort of see like what the end goal is of this problem? Hopefully. Okay. So related rates are basically, to sum them up, the entirety of their problems is just taking a weird ass situation setting them to variables and then plugging in stuff after doing a little bit with the situation, if that makes any sense. So because it's a triangle, I know that I want to model this situation using one of the many different equations that we have for triangles, right? So what do we know? We know how to find the area of a triangle. Okay, it's like area, that means something. But I'm not really dealing with the area in any sense, right? I'm kind of dealing with this length. So that I don't really think that's gonna like work. I can find the perimeter. So it's like what? It's like, shit, that's not a P. It's like S1 plus S2 plus S3. Okay. But I mean, I don't really need the perimeter, right? So that's kind of also like not really helpful. What's another like equation for the for this? There's kind of one left. How about we try something like this? Yeah. This is a right triangle. We know that, you know, this distance is going to be this hypotenuse, just changing over time as the bird flies along. This height's going to stay the same, right? So this right triangle's height always just going to be like right up like that. And then this distance, this horizontal distance, is also going to be changing over time. Yeah. So writing it out using this equation to sort of relate the different sides to each other is the best thing that we have at finding how fast this is changing. And this is sort of how, this idea is sort of how you'll be using, how should I say? Finding an equation like this to model the situation of any related rates problem is kind of like the thing to do. So for example, if you're working with rectangles and you're like trying to like do something with like the area or something, you would, in that case, you would be working with the area, because what they might do is like, okay, here's how fast the base and the height are changing. How should I say this? How should I say this? How fast is the area changing as, you know, the base is like this length and the height is this length. So that's kind of like another example. But I kind of just want to like take you through this specific example just so you guys have like one example of a problem that you guys can look over in the future. And again, I think everything's open note and there are examples in the textbook that you can like go back over. Cool. Okay. I'm going to write a squared plus b. I'm going to write the Pythagorean theorem using x, y, and z, just because I think it's a little bit easier to see sort of where I'm getting these different variables from. Sorry. And so I'm going to take each of these variables and assign them to different parts of the situation that we already have. So x is usually horizontal distance. So I can say that this distance x from the hunter to the bird along the ground, that's x. This height here is staying constant. So I can just kind of be like, okay, I know it's going to be y. Cool. And I mean, that's normally how height works, right? You know, it's like up and down, vertical. And then even though z is normally like some other axis, I'm just going to say z is this absolute distance from the hunter to the bird, which basically serves as a substitute for the hypotenuse of the triangle, right? Okay. So maybe something that we should sort of find out first is when we have, you know, this height of y, that this distance between the hunter and the bird and the hunter, z, we want to know, just to sort of start out, what actually, we want to know just to start out what what x is going to be, what that horizontal distance is going to be. But I don't want to find that just yet because I haven't really explained why you need it in a sense. Sorry, like this is so like hard and like broad. I'm really just trying to like go very slowly through it. We don't have much time. I'll get through this problem though. Okay. So right now, the three components of our equation are, we got x, we have our y part, and then also our z part, yeah? So what is this problem ask? One of you tell me what like the problem is asking us to find again? So we're trying to find the rate at which the distance from the bird to the hunter is changing as we go, as you know, the distance between them is at the specific point, right? So which of these variables in here sort of correspond to that distance between them, to that rate of change between them, rate of change of the distance between them? Well, x isn't really the distance between them, right? Because x is along the ground. It's not that like total distance, so we can't really do that. Y is just the ground to wherever the bird's flying, so that doesn't really work. But z, on the other hand, correlates directly with what we're trying to find, right? So some distance z is the, again, distance between the hunter and the bird. And we're trying to find the rate of change of how fast z is changing. We're trying to find the rate at which z is changing at some specific moment of like this. So, I mean, hopefully when you sort of think about rate of change, that sort of derivatives sort of pop into your head, right? Because as we know, you know, if we have some position s of t, the derivative of s of t is velocity, right? Does that sort of ring a bell? Yeah. So in this case, we have a position in meters units, right? So we're working with meters. And then velocity, we have, it's usually like some distance over time, right? So in this case, we have minutes. This could also be like miles per hour, so miles hour, right? Or meters per second, however you want to write it. So this relationship sort of tells you that we need to take the derivative of this equation to then find what the rates of change are for each individual part, right? So what we're trying to find is the rate of change of this. And we've actually already been given a rate of change of one of the variables, right? We've been given this, how fast x is changing, yeah? So if we have like s, you can also write like s of t as like ds over like dt, right? Does this sort of like show you anything? Does this sort of like make you remember anything? This ds over dt, that's sort of being like, okay, what is the rate of change of the position given a time t? Yeah? Does that make sense? So if we're given this rate of change of x at some time t, we can sort of write this as this dx by dt, right? Which basically just is a variable to represent how fast x is changing. Because it said in the problem, the bird is flying at that distance, at that speed, I mean, sorry. So how we're all gonna like relate everything together, I know this has been very long-winded, is we want to take the derivative of this equation that we have down here using implicit differentiation in a sense, to then basically get a bunch of these values to plug in and then eventually solve for what we're trying to look for. I'm gonna erase this. I need more room. So how do we want to go about finding the derivative of this? If you guys just want to work on it for a little bit, that's totally cool too. I can start writing it out, but don't make that. We still have much time. Does what I've written up here at all make sense? Do you see how I've gotten that? Yeah, because each of these variables, x, y, and z, those are all functions of time. Yeah. So because of that, we're kind of implying chain rule in a sense where, you have your x squared, you do the normal, okay, find 2x, and then you have to multiply it by its derivative again. But we don't know what that is yet. We haven't plugged those values in. Yeah. So you basically it's basically the same thing as implicit differentiation or like a chain rule of something that you don't like know yet, if that makes sense at all. Okay, cool. So which of these 6 variables are we trying to solve for?
X. Or are we solving for Z?
So
we don't know X.
So we are trying to solve for X, like we don't know what that is, but that's not like the end goal of the problem. So which of these is like what like the end goal of the problem is sort of like trying to get us to? Because the end goal states, okay, we want to find the rate at which the distance from the bird to the hunter is increasing. So which variable, X, Y, or Z, corresponds to that distance between them?
Z.
Z, yeah, exactly. And so which of these different things that we can plug into, which of those relate to the rate of change of Z? It's dz by dt, right? So that's kind of like telling us the rate of change of how the distance Z is changing, right? That's telling, well, the rate at which the distance Z is changing. Similar to how this 500 meters per minute was telling us the rate at which X was changing as the bird was flying. Yeah. Okay. So we know we're looking for dz by dt. Okay. So the only way to do that is if we kind of have values for the rest of these. So we need a value for X, we need a value for dx by dt, we need a value for Y, dy by dt, and Z. So it's kind of a lot of variables to plug in. But luckily, I think we can figure it out. So let's start with X. How are we going to find this X value? Well, we have this equation down here, right? We have this x squared plus y squared equals z squared, right? And we were sort of already given these 2 distances in the problem, yeah? Which is this 80 and 100. And so you can kind of just infer, okay, maybe I should just plug these two into this equation, and then I can solve for the third. That makes sense. So that's exactly what we're going to do. X squared plus 80 squared equals 100 squared. This actually ends up being 60, I believe. If you want to check me on that, like, you're welcome to.
It is.
I got
60.
60.
Cool. Thank you. Awesome. So now we have X. Awesome. We're like done with one of them. Where do we find this dx by dt? I kind of already wrote it on the board. It's that rate of change of X, right? Also given in the problem. Okay. So we have two of them down. How about Y? You're given Y, right? Okay. What do you think the rate of change of Y is? What's this dy by dt? How's the height changing? Or is it changing at all? You know, the bird is just kind of like moving in a horizontal line, right? But it's at like really high up. So because of that, we can say that because 80, this 80 value never changes as the bird flies along, it just stays constant. But that by constant, I mean it's actually just zero because there is no rate of change of the height of the bird, right? Okay. Cool. So we can write that in as 0. So we have these four. Now we just need this last one, z. But we were given that in the problem as well. It's 100. So we use these two to find this one. We were given this one. And this one we could infer because of how we knew the height wasn't going to change at all. Cool. So that kind of like itself out. And so from here on out, this is sort of where that whole plugging in part comes in. So I can basically just take all of these 5 values. Yeah, 1, 2, 3. Oh, yeah. 1, 2, 3, 4, 5. Plug them into this equation and then solve for my dz by dt. Yeah. So what do I get here? 60 times 500 plus 2 times e times y equals 3 times. Sorry, I feel like I can barely read that. Okay. Oh, is that like 1,000? It's like 6,000? Oh, 120 times 5. Yeah. 5, 6. So I think that's right. I haven't like checked it with anyone else, but I'm like 99,000% sure this is correct. Is this what you guys got when you plugged everything in? Can you hear me when I talk quietly like this from over here?
I got 300.
That would honestly make more sense. Isn't this so dy by dt is 0.
I think you just forgot to multiply.
Oh,
Like-
there's a 2 here.
There's a 2 there, and then the x part is supposed to be 60,000. Like when you multiply 2 times.
Oh, 60 times 500. Is it? Oh, is it
It's
30,000 and not 30? Is it
I
not
thought it was 2 times 60 times
Yeah.
500. Like the way that I plugged it in, that's
Oh yeah, you're right. So you get 60,000 and then this is 200.
Yeah.
Okay, and then that's what, 300?
Hmm.
Okay, cool. Sorry, did not check that. But yeah, so that's how fast the distance is changing at this specific moment. So yeah, I know that was like really long-winded and complicated, but if I could just give like a basic overview of how to do these kinds of problems, first thing to do, you write it out. You just draw everything and assign your givens to different variables, like in the picture. Okay, that's like your first step. Your second step is to find some equation, whether it be like the radius of a circle or the area of a circle or the area or like the perimeter of like a rectangle or the area of a rectangle or square or something with triangles or maybe even volume. I know volume is also a possibility. So like the volume of a cylinder would be like, the radius times the height, something like that. Or like that, no, that would be the area times the height, stuff like that. So you got to think of some kind of equation to base it off of. And then you take the derivative, often with respect to time, of everything. And when you do that, you have to multiply by that rate of change after you just do like the normal, like, okay, put the 2 down, put the 2 down, put the 2 down, right? And then from there, you just need to like find values to plug into that final equation and then solve. Yeah. So I know there's a lot of moving parts, but that is how you do every single one of these problems. It's the exact same like mindset and step-by-step process, just with different examples and different equations and different numbers. So I think that's sort of a good overview of how to do those. Does that help in any sense? I'm sorry if I just like wasted a bunch of your time and that still is like really confusing.
No, that makes sense. Like the steps that you said to go through.
Cool. Yeah, I recommend like sort of like tackling some of these problems on your own, and then you can come tomorrow. I'll probably do like an optimization problem. I know that's big, as well as like L'Hopital. I can do those. So yeah, so like these steps, honestly, literally like numbering them out, like writing out like this and then this and then this, that, and then just memorizing that is like the best way to go about it. So yeah, that's sort of everything.
Thank you.
Okay. Hope you guys have a
Have a
good
good night.
Thanks for coming. You as well.